Alright, time for a slightly new topic, confidence intervals for proportions. Now, we haven't really discussed proportions in the course so far, but the good news is that you already know all about them. A proportion is just a percentage of a population that meets a certain criteria. This can be the percentage of cars on the road that are electric, the percentage of parts on a manufacturing line with a defect, or the percentage of people in the world that attended high school. And guess what? You can use the z-distribution to calculate confidence intervals for proportions based on a sample. All you need is a variable that has two possible values, so it either meets the criteria or it doesn't. Now, I mentioned that these are categorical variables because they are. You won't be adding them up or multiplying them, but you can transform a numerical variable so that it meets this condition. Let's say you want to see the percentage of people that are overweight. Well, you can use a numerical variable like the body mass index and then just split it into two categories: BMIs that classify as overweight and then those that don't. So, how does this work in the context of confidence intervals? Well, first we need a point estimate, and for proportions this is easy. We have a p-hat, which is our sample proportion, and that's just equal to x divided by n, or the number of successful outcomes, or values that meet the criteria, divided by the sample size, or total number of values overall. And to go back to our overweight example, if we wanted to get the proportion of people that are overweight, just divide the number of overweight people by the total number of people. Right? That's how you get a percentage. Alright, so that's the point estimate in our confidence interval formula for proportions. What else is left? Well, you guessed it, the margin of error, which as always is just a critical value for the confidence level multiplied by the standard error. And this is simply the formula for calculating the standard error for the sampling distribution of proportions. And finally, important call out, you do need to check that both p-hat times n and 1 minus p-hat times n are greater than 5 in order for the central limit theorem to apply here. Now let's see an example from our project. Let's say that we want to calculate the percentage of graduates that we can expect to come with previous work experience. Well, if we go by our sample, then the proportion from our first class is 0.242 or 24.2%. And then 1 minus that, which we'll need for the standard error, is 0.758 or 75.8%. So let's say that we want to calculate a confidence interval with a 90% confidence level. So we'll need an alpha of 0.1. And with that, we can start plugging in the numbers that we know. We have p-hat, which is 0.242, and 1 minus p-hat, which is 0.758, and we also know the sample size. So let's add that to our formula. And now what we need is the critical value, or the z-score, at alpha divided by 2, and we can use norm.s.inv to calculate that. So now we can plug in that 1.64, and voila, we get our margin of error and the confidence interval. So we can expect, with a 90% confidence, to get between 17 to 31% of graduates with previous work experience, which, to be honest, doesn't seem like much. Now let's head over to Excel and work through this same example. So I'm going to go to the link on confidence intervals for proportion, click on that, and again we want to see what percentage of students we can expect to have previous work experience. So let's start by calculating the sample size. That's just going to be the count, but I need to use count A since these aren't numbers and count only works for numbers. We've got our sample size of 94. The P, remember, is the number of successful outcomes divided by the sample size. In this case, successful means that they do have previous work experience. So we want to use count ifs, and we want to count the number of students here that have yes as their previous work experience. It's going to be 23, but that's just the count. We want the proportion, so we need to divide by our sample size, which is this right here. And we get the proportion of 0.2421. And for 1 minus p, well, we just do 1 minus p and get the complementary 0.7579, which is the percentage of students that don't have previous work experience. Now, before we go any further, let's just test if these two conditions apply. So we need to do p times n. We get 23, which is greater than 5, and then 1 minus p times n. We get 72, also greater than 5, which means that the central limit theorem does apply here. So we can continue with our confidence interval. I'm going to stick with the confidence level of 90% from the slides. Alpha would be 1 minus that 90%, and alpha divided by 2 is 10% divided by 2, so 0.05. Now for the critical value, we have z at alpha divided by 2, so we're using the standard normal distribution, which means norm.s.inv. And we can do alpha divided by 2. I'm going to do 1 minus alpha divided by 2. We get a critical value of 1.64. And the standard error is going to be the square root of p times 1 minus p. So p times 1 minus p divided by n. Close my square root. This is our standard error, so about 4.39%. We can change that here if we want to. And the margin of error is just the critical value times the standard error. So our confidence interval is just, again, our point estimate, or p hat, minus the margin of error, and then the point estimate plus the margin of error. And again, we get an interval between 17 and 31%. Okay, time for an assignment on confidence intervals for proportions. Nick is back with another email, but now regarding graduate placement. Now, he loved the work on the salary data, but now he wants to focus on the students actually getting placed. So it looks like we had around 55% placement from our sample, but he wants to know if it's possible that the population proportion actually dips under 50% and wants an estimate with 95% confidence. So key objectives for this one: 1, calculate the sample proportion, which it looks like Nick already did. 2, check if the central limit theorem applies. 3, calculate the margin of error. And 4, set the limits for the confidence interval. So good luck. Alright, we've made a lot of progress so far in being able to estimate population parameters by using sample statistics, but we've only focused on a single population or a single variable at one time. But you can also create confidence intervals for the difference between two population means or two population proportions. Now, there are two possible scenarios for this. Your two populations can come from dependent samples or independent samples. Independent samples, the sample subjects or the observations in the sample are directly related to each other. For example, if you want to see the difference in people's weight before and after a diet, then you have two populations, one with weights before and one with weights from those same people after. And since it's that same group of people on both sides, then the weight measurements are dependent on each other. They are paired by each individual. Another example is testing a group of patients' blood pressure before and after taking a certain pill, but it doesn't necessarily have to be a before and after relationship. You can also compare something like the performance of the same group of operators, but with two different processes. The point being that the measurements come in pairs, making them dependent on each other. And it also means that both samples will be the same size. Now, as you can probably guess, in independent samples, the sample subjects or observations have no relationship to each other. For example, you can compare test scores for two different schools, or employee satisfaction between two different companies, or the salaries between the men and the women at the same company. So here, the measurements come from separate groups, which also means that these samples can be different sizes, but not necessarily. So those are the two types of samples of two populations that we need to be on the lookout for. Now, you'll also see them further split up into population standard deviation known or unknown, but we've already covered those differences for one population, so we're just going to stick to assuming that we don't know sigma, since it's the most common scenario in real life. Alright, so we know what a dependent sample is now. Time to calculate confidence intervals for them. You can create confidence intervals for dependent samples by calculating the difference from each pair in the samples and then treating that difference as one population. So say we want to create a confidence interval for the difference in population means between a student's MBA grade and their undergrad grade. First of all, we know that this is a dependent sample because each observation comes in pairs. We have an undergrad grade and an MBA grade for each student. So we can calculate the difference from each. So this single variable, this single population, is now the difference in MBA grade and undergrad grade for the same student, which means that we can use the same confidence interval formula that we know and love. Now you will notice that we do have d bar instead of x bar here, and that just means it's the mean of the difference, and we are using the t-distribution since we don't know the population standard deviation. And by now we know how to do all this. Let's just use a 95% confidence level, do the math, and we get a confidence interval between 3.3 and 7.1. And if we take a moment to think about this confidence interval, you'll notice that since the entire interval is positive, that means that the population of MBA grades has a higher mean than the population of undergrad grades because their difference is positive. Or at least we can state it with a 95% confidence. The other thing you'll notice that this is only because our difference was calculated by subtracting the undergrad grade from the MBA grade. So that's why we know the MBA grade is larger in this scenario. If we had done it the other way around, then we would have had a completely opposite confidence interval that went from -7.1 to 3.3. And I'm actually going to highlight that if we head over to Excel and do this same problem. So here in Excel, I'm going to go to the dependent samples link. And you'll see that we're asking how much will student MBA grades change on average compared to their undergrad grades. So for this question, what we actually want is to subtract the undergrad grade from the MBA grade to calculate the difference, because that's going to let us know how much they change from here to here. But if we had actually done it the other way around, let me just show you what that would have looked like. Let's apply this down. We have our single population now from our two populations of dependent samples. You'll notice again that the sample size is the same for each sample. Let's go ahead and calculate those anyway. I'm going to count these values. We need to calculate the average for our difference and the standard deviation of this sample as well. We're only interested in our difference now. This is our population that we created from these two populations. So we have our point estimate, our standard deviation. We used a 95% confidence level in our slides, which represents an alpha of 1 minus that, so 5%. Alpha divided by 2 is going to be 0.025. Now the critical value is t here, since we're going to use the sample standard deviation. So we need to use t.inv. We can use this probability or 1 minus. And the degrees of freedom are just the sample size minus 1. Close that, press enter. The standard error is going to be our sample standard deviation divided by the square root of our sample size. And for the margin of error, critical value times standard error, and we get 1.88. Again, we could have also used confidence.t. We have alpha, sample standard deviation, sample sized, and we get 1.88. So our lower limit, point estimate minus margin of error, upper limit, point estimate plus margin of error. So now you'll see that our confidence interval is fully negative. And what that tells us is that we can be 95% sure that the mean undergrad grade is between 3 and 7 points lower than the average MBA grade for our population of students. And let me just swap these around so you can see the difference. D6 minus C6, enter, apply it down, and now we get the positive value that we had before, which in this case answers this question a little better. Alright, time for an assignment on dependent samples. It looks like Nick is back after we gave him the bad news on our estimate for the proportion of placed graduates and wants to see which factors to dig into deeper. So, looking at the employability scores, it looks like on average our students are improving by 50 points on their results. Could you get me a confidence interval with a 90% confidence on this? Alright, so key objectives here. Number 1, to calculate the difference between the dependent samples. Number 2, to calculate the sample mean and standard deviation from the difference. Number 3, calculate the margin of error. And number 4, set the limits for the confidence interval.